Okay, so we have another problem here. So the nature of this problem, as we can see already, no, this is convection over a flat plate. No, so we have an array of power transistors dissipating 6 watts of powers for each, and they are to be cooled by mounting a 25 by 25 squares aluminum plate and blowing air at 35 degrees Celsius over the plate with a fan at velocity of 4 meters per second. The average temperature of the plate is not to exceed 65 degrees Celsius, assuming they transfer from the back side of the plate to be negligible and disregarding radiation determine the number of transistors that can be placed on this plate. Okay, so usually in your computers, your laptops, or in general any device that has an electronic or maybe has a computational load, usually has this transistors or maybe, well, yes, it will have at least one transistor and it will be generating heat as it is used. No? So you need to dissipate this heat through a variety of ways. Usually for lower capacity transistors, no? Or transistors that generate low heat, we can just use natural convection. But for higher rated transistors, or for example, higher specifications of CPU, no, that are sometimes less efficient, no. Sometimes it is less efficient than the others, no. But in general, if a transistor or a CPU, for example, has a high heat generation, no, you will also need forced convection. That is why you have cooling fans in your laptops and your computers or PCs or Mac. No? So in here, we want to design how many transistors can be placed on the plate. No? If it is not to exceed 65 degrees Celsius. Okay. I mean, it is dissipating 6 watts of power and it should not exceed 65 degrees. So how many number of transistors can be placed here? No? In this condition, you have 35 degrees Celsius at 4 meters per second on this 25 by 25 aluminum plate. Okay, so let's begin with, again, solving for, well, the H. We need to solve for the Nusselt number. So we should start with solving for the Reynolds number to determine if it is purely laminar or mixed. No? So if this is for a flat plate, we need to determine TF. So TF here is TS plus T infinity divided by 2. Ano? So you have 65 will be the temperature of the surface. No? And T infinity is 35. So the average of that 2 will be, so that is 100. No? So TF is 50. So 50 degrees Celsius. Okay. So 50 degrees Celsius, we have this as our properties, no, that we will be using. So we need to first find the Reynolds number for this length. So this will be, we just use velocity and then the length, no, over the kinematic viscosity. Kinematic viscosity. So kinematic viscosity given, the length of the plate is given, so we have 25 centimeters. So plugging things in, so we have 4 and then the length is in meters, no, this should be 0.25 meters, and then divided by the kinematic viscosity, 1.798. No? So be wary always of the units times 10 to the negative 5. So the Reynolds number, so we want to determine if this is laminar or turbulent first, no? So that we can use the appropriate formula that is needed. So you have 4 times 0.25 over 1.798 negative 5. Okay. So 55,617, no? So 55,617. So this is less than 500,000, no? So therefore, 5 times 10 to the fifth, no? So therefore, this is purely laminar. Pure laminar flow. Laminar flow. Okay. So what's next, no? What's next? We can use the respective formula for purely laminar to find the Nusselt number. So the Nusselt number, the average Nusselt number for purely laminar is 0.6, no? 0.664. And then Reynolds number raised to 1/2, and then Prandtl number raised to 1/3. Okay. So sorry, this should be with L. So we need to solve for the Prandtl. Actually, we already have a value here for the Prandtl number. So we need to find the H. So we can equate this with HL over K, which is basically just the Nusselt number. So we need to find H here. So H here is equal to K over L. No? And then you have 0.664 RE 1/2 or 0.5, no? PR raised to 1/3. Okay. So H here can be solved, no? I think we'll just solve this directly. So you have K. So K here is the thermal conductivity 0.027735 divided by L. So L natin ay 0.25, no? And then you have 0.664. Reynolds number, so 55 times 55,617 raised to 1/2. Okay, times Prandtl number 0.7228 raised to 1/3. So the answer for H is 15.37. Okay, 15.37 watts per square meter Kelvin. So finding H, we can now find the Q, no? So we just want to find how what is the total capacity, no, in convective heat transfer. So what is the maximum heat convection transfer that can be received by this plate? So we just want to find the total, and then we can divide this by the number of transistors that can be or the capacity of the transistor to find the number of the total transistors. So to find the convective heat transfer, this is just HA times the temperature difference, which is T infinity minus Ts. No? So in this case, it will be negative, but it is all right. No, it can be swapped. No, basically, if your convective heat transfer could be negative or positive. No, so it could have a direction going or into the body. So anyways, I'll just make things positive. So this will be just Ts minus T infinity. Okay, so I'll just make things positive though, but it doesn't really matter in this context if this is negative or positive. So H here is 15.37. The area is also given. No, area is given. No, so the area here is just length times width. No, so the width is 25, the length is 25. No, so you just have to convert this in meters. So let's just solve this directly in the calculator. H, no, or the answer times 0.25 squared. So this is a square multiplied by 65 minus 35. So the heat dissipated is 28.82 or 83. 28.83. Okay, in watts, no? Okay, so this is the total capacity, no? This is the maximum that can be rejected using this condition of air at this temperature of this area, no? So we just want to determine how many capacitors can we put with this 28.83 watts of budget. So we can just divide this, no? So the number of transistors is equal to the Q convective, no? So the total convective over the power of each transistor. So we have the Q of the transistor, no? Per transistor. So you have here 28.83 divided by 6, no? So the N here, how many can be put, no? So we have 4.8. Okay, so 4.8. So we can have you can have 0.8 of a transistor, no? You can either have 0 or 1. no? So therefore, the maximum that you can put is therefore 4 transistors, no? Okay? So that's it for this problem. Thank you guys for listening.